unfortunately, solving differential equations, well, as long as they are ordinary in first order, possible to do, easy, some training, and okay. Second order ordinary differential equations, some training, okay. Higher order ordinary, well, then it sometimes gets already quite hard. When we talk about partial differential equations, so a function dependent on more than one variable, two or more, well, this is really a lifetime project sometimes, yeah, to find solutions of these guys. And fortunately, for this particular type, there exists a closed form solution. So we will find a function v that is solving this partial differential equation. Today I will not show you, because otherwise we are here until midnight. I will do this in one of the next classes. What I will show you today is, I will show you the solution. How does the solution of this differential equation, so the v function, looks like? Yeah, let me check.
This is a really good question. When we talked about, so now I understand that the Black-Scholes model is kind of variation of the delta hedging. And when we discussed delta hedge last time, one thing was not clear. So when we are short selling stock underlying at the price of strike price, right? We just assume that. But, you know, the graph that you uploaded later.
Yeah.
You said S equals K, right? And the short selling graph was passing by K on x-axis. But in real life, it's not really the case. It cannot really be that way, right?
Why not? It can.
But what if it ends up being, what if you buy underlying stock? Because the underlying stock is the same stock as your option underlying.
Right.
Right? So what if you short sell that stock at different prices? What if your price of the stock at that very moment is different from the strike price? Then, because the graph that you uploaded actually shows that there's always positive profit. But
yeah,
in the examples, for instance, in your lecture note,
yeah,
shows that there's only positive payoff all the time, not necessarily profit. But it is always positive profit if short selling is executed at the price of strike price. But if not, then it's not true.
That's right. That's right. But anything what you explained regarding delta hedge, you know, what we need here is just this idea that the number of C2 of stocks in this portfolio is chosen according to this function, which we don't know. We have to find this function by solving this equation. But as long as we have this function, we calculate the first derivative, which is a number in the end, the slope. Well, if we choose this amount of stocks in my portfolio, then I can eliminate the risk. And that is a pure idea to get a price of an option, because we are getting rid, by this trick, we use the delta hedge to find the price of an option.
Okay.
Yeah?
And this delta hedge is delta amount of stock, but so delta amount of delta stock.
The delta, so next week we will talk about what is really the delta, because when we have the function, I can compute the delta for the first time. So far it's, you know, something in the blue. But the delta in the end is a number, it's a slope. Obviously, dependent on where the stock price is, the slope of my option price function is different. But the delta gives me a number, it could be 1, it could be 5, it could be 5.7. And this is a number then of underlying assets we need in this portfolio to get rid of the risk. Yeah? So we will come back on this delta, and hopefully it gets clearer then at that point. But anyway, if you have questions, we can discuss this later on. So let me talk about the solution, right? That is my next step. Solution of this differential equation? Well, interestingly, as I already mentioned, for this special type, there exists a closed form solution. For most of the financial products, well, if we have not plain vanilla options, like we assumed here, so if we, for instance, assume American options, or exotic options, which we will talk about in one of the next classes as well, you always have to derive for all the different option types, you have first to derive this equation, this Black-Scholes equation. And for every option type, this equation looks different and obviously more complex than for the simplest possible case we are tackling right now. And for most of these other cases, these American and exotic options, there exists no closed form solution of this partial differential equation or modifications of this. And then what you can do, to find a price, to get a solution, well, you have to do numerical approximations. That's a new class, right? Scientific computing, how to solve numerically partial differential equations. And that is what what we can do in MATLAB with this software product, to find approximate solutions of complex partial differential equation. And that is important because the more complex financial products, they have no closed form solutions. You can only get an approximate of these solutions by numerical computing. So many people trade derivative products without really knowing how does the price is computed. And therefore, this is my warning. You can also find on some of my slides. Do never trade a product you don't understand. It's never good.
But that's happening in the real world, like you already just right. So if you can't solve the whole product, but maybe there's someone else who can do it, then he might have an advantage and just makes profit out of it. So you may gain a huge loss as a counterpart to this.
If this is a product that maybe helps you to make a fortune or a profit in the end, it's good. But you always need a counterpart, right? As long as you find not a counterpart, you cannot gain or you cannot lose. And obviously, if the product is very complex, and therefore that's my warning. Do never buy or sell such products which you cannot understand. Because if they cannot really find a counterpart, but that is what they did during that time, right? That was before the start of the financial crisis in 2007. Everyone was just looking on how can I get a high rate of return. They have not bothered really on what is in and what is the product about and how does it behave. So it's just some crazy people in engineering departments maybe acknowledged and know something about these properties of this product, but this is the risk, right? If you trade products you don't understand, and therefore it's a highly risky business. And well, I have not asked him whether they did it really, but so he was really happy to, and that is what he said to me, that now we can use and start trading with this financial product. No. It was one of the big German investment banks, and probably there is just one, which is also impressed at the moment, right?
But what's actually then the real benefit to the real economy of those products?
There is no benefit, and I'm not advertising these products, and I'm not interested in these products. I'm just interested in the mathematical problem.
So basically, those products who actually don't have any benefit to the real world crash the real economy?
Absolutely. Yeah, that's one of the lessons we talked about in macro. Hey, come on, yeah. So actually, maybe we can talk also about this towards the end of this class. I'm convinced that finance is an instrument for the real economy and not for itself. And in the recent past decades, finance got a field which was really disentangled, disconnected to the real economy, which is wrong. definitely. Okay, so let me come back to the solution. Well, so in my lecture notes, by the way, there are several ways demonstrated how you can solve this. One is, for instance, a Fourier transformation. One is you can transform this to a heat equation, this one. A heat equation is a famous problem in physics. We already know the physical answer of a heat equation, and then you do the retransform, and then you have the solution of this. You can also solve it with so-called Lie algebra, which is also my lecture note, which is the craziest approach I have at the moment. But it's anything. It's interesting, and I will show you next time another approach how to solve this. Let me write down now, without showing, the solution for my function v. So, how does the solution of this look like? So, my function v, solution of this partial differential equation is the following. It's S times normal distribution at D1 minus strike price K discounted with the risk-free interest rate R time to maturity, T minus T, times the normal distribution at a parameter D2. So how does the normal distribution in general look like? So I used now a general letter X for D1 and D2. So this is, as we already know, it's 1 over the square root of 2 pi. Integral from minus infinity to my boundary variable X, e s squared over 2 ds. And now I have to tell you what is this x, this d1 and d2. And then we have the solution completed. So the d1 and d2 consists of the following terms. It's a natural logarithm, so it's the ln of stock price today divided by strike price K, plus risk-free interest rate R plus minus sigma square over 2 T to time to maturity T minus T, and in the denominator we have the volatility sigma square root of T minus T. This is the solution of the Black-Scholes equation, which is here on the bottom. This is the solution of the Black-Scholes model, solution. And I think it's obvious for everyone that the solution, even the solution, is highly complex. The first you have to notice is the following. A solution of a differential equation is always a function. Right? For our population growth model in macro, it was a function how the people behave over time with exponential growth. And here it's also a function. What are the elements of this function? Well, this is what we have to look at. So first of all, this function has to converge to S at capital T, right? To S minus K. Well, if T is equal to T, well, this gets away, right? 1. This is 1. So what remains? I guess you see it immediately, that is St minus K, because the other terms are 1 at the end of maturity, right? So we are in line with my boundary conditions at the end of maturity. At capital T, S capital T minus K. This is 1, this is 1, this is 1. So we are right. That is the payoff function we already used at time at capital T. And that is inherited in this solution function. These normal distribution, right? And therefore we discussed it. We had one class where I just recapped expectations and how does a normal distribution look like, right? This is, I don't expect that you really recall this by heart, but that you remember, that is what I hope, right? That this 1 over square root over 2, this integral, that this is the density function, or when we integrate, the distribution, the normal distribution, right? This is the density, and when we do the integration, we get the distribution, the normal distribution. That is this. And we have these tables in statistics books, so we can find this for any x, yeah? We get a certain probability, a certain number for this normal distribution. And this x is either a d1 and a d2. For d1, we do the plus. For d2, we do the minus. And this is the terms how to get the d1, d2. Then we bring it here in the distribution. Then we substitute these numbers here in nd1 and nd2. And then we get a final value of v. There's another interesting point. Take a look. All the parameters on the right-hand side are given today. So we find the option price function, right? That is giving us a value in the future, right? We exercise this in the future, and we don't know what the stock price is at the end of maturity. But all the parameters are given today. This is the stock price today. This is the strike price, which is fixed in my contract today. Risk-free interest rate is given. Time to maturity is given in the contract. And also the D parameters. Take a look. Stock price today, strike price, given. Risk-free interest rate, time to maturity. Volatility, sigma. Well, volatility, you can just say, let's take a look of the volatility of the underlying of the past. That's what we call the historical volatility. And we plug it in. So all the numbers in the end, all the numbers are given today. So we can plug in the numbers we have for Microsoft, for Nike, for Apple, and we will find for the different strike prices then the price of my option. And actually, all the calculators, the option calculators, I'm not sure whether you have also looked to this option calculator in FactSet. There is one implemented in FactSet, an option calculator. But you can also find option calculators in the internet. So if you Google for option calculators, all these option calculators, if they compute the analytical, numerical, precise solution, behind these option calculators is this formula. And you just plug in the numbers, right? There's a cell where you write in what is the stock price today, what is the strike price is 100, risk-free interest rate is, let's say, 1%, volatility is 10%, time to maturity, let's say, is a year. Yeah? You plug in cells these parameters, you click on enter, and then it does a computation, and it tells you what is the price the price for this option function, call option in this case. This is the formula for the call option, European call option. As I already mentioned, in many cases, this closed form solution, which I wrote down here, does not exist. And then all these calculators are not based on a closed form solution, they are based on numerical procedures. Yeah, and most of the calculators you find in the internet, they use numerical approximations of the true option price. Let me add at the end of today's lecture one final point. How does the Black-Scholes solution looks like for a put option? The equation is the same for a European call or a put option, but the solution is different. Why? Because for a put option, my boundary condition right, is the opposite. It is K minus ST plus, right? This is a boundary condition at the end of maturity for a put option. And therefore, how does the solution look like? Well, in the end, let's write down here, it's for a put option, the solution, for the put option dependent on the underlying and my time, it is K discounted minus R t minus t at d at minus d2 minus st at d minus d1. And d1 and d2 is the same as in this case here, and the normal distribution is the same as written here. And by the way, if we are able to prove, what I will do, if we have enough time, this for the call option, that this is the right solution for this equation, then the proof for the put option is quite simple. Can you imagine why? Why is the proof, if we know that the call option is right, why can we then say that the put option, or to find the put option price, is quite simple? Why?
With the put-call parity.
Put-call parity, that's the trick. The put-call parity, if you remember, that's put, if we have, if we have a put option, the put option plus the stock minus the call is always this risk-free portfolio. That's a put-call parity. So if we know this, right, then we just put these two terms on the other side, and then you can verify that this is the solution. So if you bring the S on the other side, if you bring the C on the other side, and for the C, write down this equation, this first line, and then you can simplify, and you will see immediately this pops up. This is a very simple proof. 3 steps, and you did it. Okay. So what we did today is we derived the Black-Scholes equation. That is this box, which is an equation dependent on this function v, which is my option price. I told you there exists, for this case, a solution, which is written here on this as an equation on this whiteboard. And now at the end, let me show how this function, once again, looks like in graphical form. Final minutes. So the graphical representation of the mathematical formula I wrote down a minute ago is actually this 3-dimensional function, and I will just rotate this function that you can see a little bit how this function looks like. You know, it's a 3-dimensional function. It's dependent on my underlying price S time t, and on the set x, basically I have the call option price. And for every time to maturity and for every certain stock price, you will find a different price of the option. And this is the function you obtain if you simulate, if you graphically illustrate this mathematical formula we first derived and then solved today in this class. Okay, so I hope you have learned something about Black-Scholes today, and next time we continue at that point. We will discuss the Greek letters, which are sensitivity parameters, and then we go on to exotic options and some other pricing issues in financial markets. Bye-bye.